Hello everyone. So today we will study about the rotational motion, some practice problems. First problem we have is the three objects are located in a coordinate system as shown in this figure and find the center of mass for this. So we have x-axis, we have y-axis here, then we have these three objects. One is 2 kilograms, which is at the origin. One is 4 kilogram, which is on the positive side of x-axis. And we have 5 kilogram, which is on the negative side of the x-axis. The y-coordinate and z-coordinate of the center of mass are 0 because both the objects, all these even three objects, they are lying on this x-axis. So the x-coordinate of the center of mass has this formula that summation of mi xi is divided by summation of m of I. Mi means all the different masses, xi means all the x distances from the axis of rotation. So here we have three masses m1, m2, m3, and we will check their respective distances from the axis of rotation. So guys, in this the important thing is your axis. Okay, so when you will check this diagram, this figure, so your first mass is 5 kilogram and this 5 kilogram is at a distance of 0.5 meter towards the negative x-axis. So we will take x1 equals to negative 0.5 meters. Now 2 kilogram is lying on the origin, so its distance from the axis of rotation is 0 because it is at the origin. And 4 kilogram mass is 1 meter from the origin, so its distance is 1 meter. Divided by summation of mi means just the sum of the masses. So 5 kilograms plus 2 kilogram plus 4 kilogram. If you just plug in the number, do the calculation, so you're going to get the x coordinate for the center of mass and you will have 0.136. Now second part for this first problem is, how does the answer change if the object on the left is displaced upward by 1 meter and the object on the right is displaced downward by 0.5 meter. So our new diagram will be like this, that 2 kilogram is at the same position and the 5 kilogram is now 1 meter, is here 1 meter above this axis, and the 4 kilogram mass, so this is basically our 5 kg, and this 4 kilogram is 0.5 meter downward to the axis. So now the location of our three different objects is this. 2 kilogram is at the same origin. Your 5 kilogram is at this position, which is 0.5 meter from the x-axis and 1 meter above the y-axis. And this 4 kilogram is 1 meter on this side and 0.5 meter from this side. So now for this position, the center of mass, it will have its x coordinate as well as the y coordinate. We have the same formula, center of mass, x coordinate, summation of mi xi divided by summation of mi. So we are just going to plug in the same numbers for this x coordinate and you will get the same number for the x coordinate of the center of mass, because all the x distances, they are still the same in this figure. But the y coordinate of the center of mass is summation of m of I, y of I divided by m of I, summation of m of I. So when you're gonna plug in the numbers, so we have m1y1, m2y2, and m3y3. So now we'll check all the y distances of these objects. So if you check the first 5 kilogram object, it is at a distance of 1 meter. The next 2 kilogram is at the origin, so its y distance is 0, and 4 kilogram is at a distance of negative 0.5 meter from this axis of rotation. So we are just plugging we'll just plug in the y coordinates here, and you'll get the y coordinate for the center of mass as 0.273 meter. So this is how you are going to find the center of mass for any system where when the different masses they are located at different positions. Now you can also do one thing, like if you have a coordinate system, so if suppose if I'm talking about this 5 kilogram mass, so this 5 kilogram, if it is here at this, do one thing, just write down the coordinates for this mass, and then that's gonna be easy for you to do. So even if here, if I check what is the x coordinate for this 5 kilogram, so the x coordinate for this is 0.5, and the y coordinate for this is 1 meter for this 5 kilogram mass. So if you'll just check the coordinates for a given object, it is easy for you to find out the center of mass, because you're just going to write down all the different coordinates for all the different objects if you have in the system, and you can easily find out the various center of mass coordinates x, y, or z, whatever is required. Okay, the second question is, a torque of 25 Newton meter is applied to this rectangular object shown in the figure. The torque can act about the x-axis, the y-axis, and the z-axis, which is passes through this origin and points out of the page. Find the angular acceleration when the torque acts about x-axis, y-axis, and z-axis. So to find the angular acceleration, we need to find the moment of inertia first. So moment of inertia is basically summation of MIRI square. So here you have four masses, mass 2.5 kilogram, M2 3 kilogram, you have M3 4 kilogram, you have M3 1.2 kilograms, and you just need to check their distances as well again now. So this is the important thing again, your axis of rotation. So now firstly we are talking about the axis of rotation is when x-axis. So this is the axis of rotation right now. So you're going to check the distances from the axis of rotation. Okay, so for the first mass, which is your 2.5 kilogram, now since this is on the x-axis, so this is its distance is 0 kilogram. Then the second mass, 3 kilograms, its distance from the axis of rotation is 0.5. Then again your M3 1.2 kilogram is again lying on the x-axis, so its distance is 0. And the fourth mass, 4 kilogram, again its distance from the axis of rotation is 0.5. So this is what you need to check in these type of questions, your distances from the axis of rotation. So just do the calculation and you will get Ix, that is moment of inertia along the x-axis, is 1.75 kilograms meter square. So kilogram is for the mass and meter square is for the square of the distance. So once you have the moment of inertia value, you can find out the angular acceleration along this x-axis. So the formula to find the angular acceleration is this. Alpha x is equals to torque divided by I of x. So alpha means acceleration, torque means force, and your moment of inertia is basically the whole movement, because now the object is rotating. So the moment of inertia in rotational motion is almost behaving the same role as mass does in translational motion. So in translational motion, your acceleration is F over m. And in rotational motion, you have alpha, which is basically your acceleration, torque, which is basically your force. So this moment of inertia in rotational motion behaves the same role as mass does in translational motion. So torque is given to you. Torque is your 25 Newton meter. So 25 Newton meter divided by 1.75. So this is the answer. Alpha x is 14.29 radian meter square. Now same we are going to do for the moment of inertia along the y-axis. So same formula, summation of mi ri square, and now the only thing is you are going to check your distances of the masses from the y-axis. So your first mass, that is your 2.5, since this is on the origin, its distance from the y-axis is again 0. Your 3 kilogram is on the y-axis, its distance from the y-axis is again 0. Your third mass, 1.2, is at a distance 0.7, so you just plug in that number, and 4 kilogram is at the same distance 0.7 meter from the y-axis. So just plug in these numbers, do the calculation, and you'll get IY, that means moment of inertia along the y-axis. So once you have moment of inertia along the y-axis, we can find the angular acceleration along y-axis. So torque divided by I of y, torque is 25 Newton meter divided by the 2.55. So you'll get this number, 9.80 radians per second square. And along the z-axis now. So along the z-axis, now you're going to check all the distances of the masses from the z-axis. So first object 2.5, since it is at the origin, its all distances, whether it's x, y or z, will be 0. Second mass, which is your 3 kilogram, this will be at the same distance 0.5, since your z-axis is passing through origin and points out of the page. 1.2 will be at 0.7, but now this 4 kilogram will have the diagonal distance from the z-axis, which is coming out of the page, and that distance will be basically, so this under root of 0.5 square plus 0.7 square and under root of that, and since you are squaring this, so you are going to take out the under root. So basically your R4 is equals to under root of 0.5 square plus 0.7 square, and since you are squaring in this formula, so you're going to take out this under root from this equation. That's it, and just you will, when you're going to do the calculation, you will get your Iz equals to 4.3 kilogram meter square. So this is how you're finding the different moment of inertias along different axes, and you can also find alpha z That's going to be your torque divided by I of z, and you will get the number 5.81 radians per second square. So we got the different angular accelerations on different axes, x, y, and z. Next question we have, a 60 kilogram mother sits 3 meters from the fulcrum of a seesaw. Her 20 kilogram daughter sits 3 meters from the fulcrum on the other side. Where should her 60 kilogram son sit to balance the seesaw? Now these kind of problems, what we do, we apply the conservation of torque principle. So the conservation of torque means whenever you have this kind of balanced situation, here we are talking about this seesaw, so you have some masses on this side, you have some masses on this side of the fulcrum. So this mass will experience some torque in the counterclockwise direction. This mass will experience the torque in clockwise direction. This will experience the torque in the clockwise direction. And what is the torque basically? So torque in rotational motion is F into D. The force which is acting because of this mass multiplied by the distance, this distance from the center point. So here we are saying that this 60 kilogram mom is sitting on this side at a distance 3 meters from the fulcrum. 20 kilogram daughter sits 3 meters on this side. 60 kilogram son sits here. So you just need to find this distance D. So we are going to apply this equation that summation of torque will be 0, means in a balanced situation the total sum of torque will be 0, and whatever your total counterclockwise torque is on this side will be equals to the total clockwise torque on this side. So torque clockwise we are getting from these two masses, one this mass and one this mass. So 60 kilogram is with the distance this D, 20 kilogram is with the distance 3 meter. So 60 into 3 plus 20 into 60 into D plus 20 into this 3 meters should be equals to the counterclockwise torque which we are getting from this mass, which is 60 kilogram, and we have its distance as well, that is 3 meter. So just plug in the numbers, do the calculations, and you will get the distance D from this fulcrum where her son should sit to balance the seesaw. So he should sit at 2 meters from the center point to balance this. On the same principle, we are going to do one more question, which is find the unknown mass if the system is balanced. So suppose you have this system, here is your center point, the fulcrum is here, and now you are having four masses basically. Here you have 20 kilogram at 3 meter, 50 kilogram at 5 meter, 15 kilogram at 2 meter, and this is your unknown, and this mass is at 6 meter. So again we will apply the summation of torque equals to 0. The total clockwise torque should be equals to total counterclockwise torque. So when you will apply this clockwise torque on these two masses, you will have 15 into 2 plus this m into 6 equals to 50 times this distance 5 and this 20 times this distance 3. So just do the calculations and you'll get the mass to do the balance of this system. So this M should be 46.67 kilograms to balance this system. So these four questions were basically just about the moment of inertia, center of mass, and how to find the various unknowns by using the summation of torque equals to zero equation. Now, in this whole rotational motion, we can apply all the formulas and all the equations, whatever we have done in translational motion, all your initial velocity, final velocity, momentum equation, alpha, finding the acceleration. So we can apply all the equations in rotational motion as well. Now just the parameters change, right? So in translational motion, you were having displacement x, that in rotational motion you displace by theta. So we are going to apply the same formulas, but now only your description is different. So a ball on a string is going around a circle at 6 radians per second. 6 radians per second is what? Is your omega, which is the angular velocity. What is the velocity if the radius is 2 meter? So this is the relation between translational velocity, which is your linear velocity, v, omega is your angular velocity, and r is the radius. So in rotational motion, theta plays the same role that x plays in linear motion, and then omega plays the same role that v plays there. So omega is the angular velocity, v is your linear velocity, alpha is your angular acceleration, here a is your linear acceleration. So like this. And you can also write down all your kinematic equations using these variables. Sixth question is, find the angular acceleration if radius is 4.3 meter, initial velocity is 0 meter per second, and final velocity is 400 meter per second for 60 seconds. So we are going to apply this equation. So this is the relation of linear acceleration and angular acceleration. So linear acceleration is because rate of change of velocity, delta v over delta t, and delta v is what? Change of velocity, vf minus vi, equals to r times alpha. So r is the radius and alpha is your angular acceleration. So when we'll plug in the numbers, your final velocity is 400, initial velocity is 0, your radius is 4.3, your time is 60 seconds. So you will get the alpha is equals to 1.55 radians per second square. Next question. So you opening a door by pushing on its outer edge with a force of 100 Newton. If the door is 1.3 meter wide, what torque you are going to apply if you push perpendicular? So this is just a direct equation. Torque is equals to F dot D, the dot product of force and distance, and the dot product is FD cosine of theta. So you have the force given to you, that is your 100 Newton. The distance is 1.3, and since theta we are using 90 degree, so cosine of theta will be 1, cosine of 90 will be 1, and you will get torque is equals to 130 Newton meter. Next question is question number 8. So suppose you are rotating a ball around the end of 1 meter or iron rod, and if the ball has a mass 10 kilogram, what torque do you need to apply to get an angular acceleration of 0.5 radians per second square? So we'll apply this equation. Torque is equals to I times alpha. So that means if you check this equation, F is equals to m times A, right? So here you have torque for the force, I for the mass, and alpha for the acceleration, A. And take it out. So I is equals to, since mr square, and so my torque will become now the mr square alpha. And since I have the mass, which is 10 kilograms, my R is given to me 1, and the alpha is given 0.5 radians per second square. That's it. So just plug in these numbers and you'll get your torque 5 Newton meter. Next question is, if you have a ball of 100 kilogram with a radius of 1 meter rotating as at 10 radians per second, find the rotational kinetic energy. So now what is given to you? If you check, you have this mass, you have the distance, and you have this rotating at 10 radian per second. So radians per second means what is given to you? You have omega. So that is the angular velocity is given to you. So equation for the rotational kinetic energy is half of I omega square. And if you remember, your kinetic energy in translational motion was half of mv square. So if you check, half is the same, I is for mass m, and omega is for the linear velocity v. So just plug in the numbers, and moment of inertia is basically your mr square. So m is 100 kilograms, r is 1, and omega is given, that is 10. So the total kinetic energy you will get 5000 joules. So these questions that we are doing, these are just the direct formula questions, but just remember that you are just replacing all the translational variables with now rotational motion variables. So let's do one with the equation as well. Question number 10. A wheel rotates with a constant angular acceleration of 3.50 radians per second square. So if the angular speed of the wheel is 2 radians per second at ti equals to 0, through what angular displacement does the wheel rotate in 2 seconds? So delta theta is equals to omega I t plus half of alpha t square. If you remember, we have also done in translational motion that delta x is equals to vit plus half of a t square, right? So in this rotational motion, delta theta means your delta x, omega I means your initial velocity that we did in translational motion, t is same, and alpha is your angular acceleration, and a is your linear acceleration. So just plug in these numbers. Delta theta we need to find, omega I we have 2 radians per second, time we have 2 seconds, half of alpha is given to you, that is 3.50 radians per second square, and your t is again 2 seconds. So you will get delta theta equals to 11 radians. B part, what is the angular speed if the wheel is at t is equals to 2 seconds? So omega f, so now you need to find the angular speed, the final angular speed, okay? So initial is given to you, and you have your so omega I, you're gonna take your 2 radians per second, your alpha is given to you the same 3.50, and what will be your final angular speed that you are finding, omega f, after 2 seconds? So that will be your 9 radians per second.